So, with the basic neuroscience out of the way, let's focus on this cardiovascular physiology during non-REM sleep. And I want to go back to sort of the Eastern concept of yin and yang. And here's the fundamental concept: the distinction between self and not self. We can conceptualize self as the integrated internal representation of our being, and everything outside the circle represents the external world, the not self. And as I said, the boundary as depicted by the circle is not a rigid wall, but rather a permeable membrane constantly interacting with the external world. And what's key is that this boundary needs to be maintained for a coherent sense of identity. And this is where non-REM, specifically slow wave sleep, plays a critical role. And this is characterized by parasympathetic dominance and slow, stable, and coherent neuroactivity. And so non-REM, I propose, is the state which solidifies our self. And we see this the way the heart rate remains stable. So here's a concrete example of this. You see the autonomic stability during non-REM sleep. This figure shows data from a healthy young adult participant through a full night of sleep. On top, you have the hypnogram showing the progression through sleep stages. And below, we see the instantaneous heart rate. And if you could focus on the shaded areas represented by deep, slow wave sleep, stages N3 and N4, there's N4 because this was published in 2005. Back then, they had four stages. And you notice that in contrast to wakefulness in REM or even lighter non-REM stages, the heart rate during deep sleep is not only generally lower, reflecting sort of parasympathetic dominance, but also remarkably stable. There isn't much fluctuation. This physiological stability, this reduced variability, is a key indicator of the internal focus, the turning inward that characterizes the consolidation of self during non-REM. And this comes from another study which shows something similar. And this shows 90-second segments of heart rate on the top, which is obtained from wake to N1 to N2 and N3. And wavelets were used to calculate the spectral components of the heart rate shown below. And as non-REM sleep progresses, you see that heart rate overall decreases and the amount of dynamic fluctuations also decrease somewhat. And as a result, the total overall spectral power represented by the area under the curve in these spectral graphs decreases from wake to sleep. And so you can see that the total area under the curve is reduced in N3 compared to wake. And the dashed lines here represent the respiratory frequency, and thus the peak is associated with the respiratory sinus arrhythmia. And the darker green colors in N3 shows that high frequency, low frequency ratio is greater. In other words, the proportion of the high frequency HRV, a marker of parasympathetic, is higher. Now, this pattern of increased stability and coherence during non-REM sleep isn't limited to heart rate, and we see it in other crucial autonomic functions as well. So this left panel shows breathing patterns across sleep cycles and sleep stages. And during wakefulness, breathing is relatively irregular, reflecting our changing activity and environment. But as we progress through non-REM stages, particularly reaching to non-REM 3, the breathing pattern becomes strikingly regular, almost metronomic in its rhythm and amplitude. And you could also notice, just like the heart rate, the amplitude also decreases as well. The EEG also basically shows this similar relationship. You see the high frequency desynchronized low amplitude waves during wakefulness. As we move deeper into sleep, however, those higher frequency waves are replaced by low delta frequency waves. And these waves becomes more powerful, reflecting the increased synchronicity and overall stability. And you may notice the identical pattern of the spectral breakdown across these multiple epochs. And you can see for non-REM 3, across multiple epochs, they look very identical, whereas in non-REM 1 or wake, you can see that there's a lot of variability between each of the epochs. So now we've seen evidence of the parasympathetic dominance and increasing stability during non-REM. On the other side of the autonomic point is the sympathetic activity. And this study used microneurography, a technique that directly measures the firing of sympathetic nerves in the peroneal nerves here going to the blood vessels. And it directly measures sympathetic outflow. And the traces show sympathetic nerve activity and blood pressure during wakefulness and different stages of non-REM sleep. And you can see during wakefulness, there is decent amount of activity in the sympathetic nerves. But as you progress to deeper stages of sleep, the sympathetic nerve activity significantly diminishes. And this, directly confirms the reduction in sympathetic tone during deep non-REM sleep, further supporting the idea of a shift towards an internally focused restorative state.